Folding and faulting video 3. In the last video, we ended off with a diagram like this, which shows the map view of an area that shows geological faulting and folding. Note the information that we're given about the fault 1 dipping at 40 degrees towards the southwest and fault F2 is vertical. Now straight away you should be able to see there's an axial plane trace on this diagram. That is a point of symmetry, and I've highlighted it there in yellow. Notice if you see the central point through both of these, that line remains the same. It hasn't been displaced across this fault. However, continue the axial plane trace to the other side, to the eastern side of the map, and you can say there is clear displacement. Now, these dip arrows here, as we saw before, show that there is a syncline because the arrows are pointing in towards a central core. Notice the symmetry of the beds either side of the axial plane. We can confirm that it is a syncline because remember, in a syncline the youngest beds are in the center, and as you can see here from the key, the youngest beds are in the center of the syncline. Notice on this map though, there are no tick arrows to show the down throw side of the fault. So the question is, from this diagram, how can we work out what type of fault, reverse or normal, fault F1 is? This is the area on the next diagram we're going to concentrate on, this box here. Okay, so there it is highlighted. Notice again there's no down throw ticks. So here's this question again, what type of fault is F1? Again, the axial plane trace hasn't been displaced, so it's not a strike slip fault. So it's likely to be a dip slip fault, either a reverse or a normal. But which one? How can we work it out from this information? Well, the important thing we look at is the width of the central beds. Now you can see on the eastern side, the width of the beds here is much wider than on this side here, the western side. And that gives us a clue about the up throw and the down throw side. Now, here's a syncline. Notice the red fault here. Now, let's just say the northern block gets uplifted. There it goes. And you can see it retains the same synclinal shape as the lower block. That's the up throw side, and that's the down throw side. Over years, due to denudation processes of weathering and erosion, the large upper part of this block will get worn down. Notice what happens when it gets worn down to a similar level. Notice again the width of the central beds either side. There's the axial plane trace, so it hasn't been displaced. But look at the width of the northern block compared to the width of the southern block, that central bed there. Let me go through that again. There's the block that's been worn down. There's the up throw, there's the down throw. Watch that green central block. What happens when it gets worn down? Notice it appears to be much thinner. Now that gives us the clue about whether the fault is going to be a normal or reverse. How does it do this? Well, there's a typical, as you've just seen, an eroded syncline, the outcrop pattern. That's what it looks like on a map. Remember, there's the syncline. This must be the up throw side because it's the narrower block. There's some dip arrows there to show you what it would look like on a map. So from the information we got from before, there's the axial plane trace. We know that this block is the up throw side and this block is the down throw side. Why? Because the outcrop pattern, the central core bed, is thinner to this up throw side. And that's the key to remind yourself. In a syncline, the narrower outcrop shows the up throw side. Okay, let's apply that to our knowledge. This is the first map again. There's the axial plane trace, non-displaced. Look at the beds. This side much wider, this side much thinner. What do we say in the last slide? In a syncline, the narrower outcrop shows the up throw side. So we can fill this information in. upthrow and downthrow. So that's the first bit of information. But how can we work out if it's a reverse or normal fault? Let's just move on back to the central map again. Axial plane trace, upthrow, downthrow. Now the second bit of information that we need is a written bit of information. As you can see in the bottom left hand corner here, fault F1 dips at 40 degrees towards the southwest. Now the southwest is towards X, and what I'm going to do is show you a cross section from X to Y. Okay, here's that extract again I just showed on the previous page. There's X, there's Y, there's a tree to show you we're looking from sideways on from cross-sectional view. Now we said the fault was dipping southwesterly, that's towards X, in 40 degrees. So that's towards X, that's 40 degrees. The X side is the upthrow, the Y side is the downthrow, and also now we can work out hanging wall and footwall. The hanging wall is above the fault, the footwall is below the fault. When hanging wall equals upthrow, you know we have a reverse fault. Okay, let's apply that to an anticline this time. There are flat beds. They've been folded up into this anticlinal shape, and then over millions of years it's been worn down. You can see the oldest bed is in the core. Okay, let's fault this now. That same block there, the last block we can see here, we're going to fault it, and we're going to throw up the northern side, the far side from us. Notice the shape it makes here. Notice how much wider the base is there. So when we cut this block down, this one gets cut down here, we'll notice it's much wider on the upthrow side. Okay, let's just move it up there by the wonders of magic. Okay, and that is the outcrop pattern we would see. Notice again on an anticline, the upthrow side is much wider than the downthrow side. So in an anticline, the wider outcrop shows the upthrow side. So in summary then, in a syncline, the narrower outcrop shows the upthrow side, and in an anticline, the wider outcrop shows the upthrow side.